Good morning. Um, we are ready to move on to our next chapter. We are moving into chapter 36, Special Theory of Relativity. So up until now we've been working in terms of what we consider to be classical physics or classical mechanics. It turns out when we get down to the level of particles, a lot of times these particles are operating at high energies, high velocities, and the formulas that we've learned through Newtonian physics are not going to be adequate anymore. So we're going to have to take a closer look. Now here are the units in chapter 36. And again, I'm going to go through these pretty quickly. I do want to comment on this. There's a number of sections early on where they go through and talk in some detail about relativity and give some examples of deriving some of the formulas, and we're not as interested in that as we are in learning how to apply the formulas of special relativity. So you are welcome to read through those early sections in the chapter, but I think if you look at the homework assignments and I think if you look at the sample problems that we have here in lecture that we're going through, these are going to show up in some of the later sections. We do want to get some kind of a foundation here though, so let's do that. Relativity suggests this. In classical physics, there is this concept of relativity, and the idea is if you come up with some coordinate systems, so here's a couple different coordinate systems here, and as long as those coordinate systems are moving at constant velocity, we consider those to be inertial reference frames. So in the diagram that we have set up here, what we've got are inertial reference frame S, and we're calling this one S prime, and we put some X, Y, and Z coordinates here and X, Y, and Z here. And then we've got a relative velocity set up here. Now, what we found all through Physics 4a and Physics 4b really is that if we're moving at a constant velocity, all of those formulas from classical physics work. Down at the bottom, this is just a reminder that objects are either moving at constant velocity or there's an acceleration taking place. It's one or the other. Those are the only two categories of motion that there are. Something at rest has constant velocity. Now, just a reminder here in the middle, Earth is rotating, Earth is orbiting, so there are these small accelerations taking place due to the motion of the Earth, but in many situations we do treat the surface of the Earth as if there's no acceleration. It turns out that for many situations it's a small effect. So here we go. Relativity says this. Here is this car moving along the highway, and what we're going to say here is that the car can either consider, let's look on the left. On the left we're going to say that the car is considering itself to be at rest and it's watching the Earth go by. Now that's kind of an interesting way to approach this, right? I'm driving my car down the highway. As long as I maintain constant velocity, I'm an inertial reference frame. My coordinate system works just fine. So in my coordinate system, the surroundings, the outside, is moving past me. So that's one reference frame. And then of course the other obvious reference frame would be the one with the Earth. So in this one, the Earth is at rest and it's the car that's in motion. Now it turns out that, see this person drop something out the window? I guess it's got to be something biodegradable or something anyway, a rock or something. So it's a passenger, it's not the driver. Driver is not being distracted by this. So this person has dropped something outside the window, and notice that in the reference frame of the car, that object just drops straight down. You know, I let go of something and the object just seems to drop straight down from where I've released it. Now remember, the outside in this reference frame is moving past the car, And if we switch now to this other reference frame where the Earth is at rest, then what the observers in that other reference frame will observe is that that object the person dropped had an initial velocity in the forward direction. So they're going to measure this parabolic motion, something that should be familiar from Physics 4a back around chapters 3 or so. So that's like projectile motion, right, with an initial velocity. Well, this is just a straight drop because there was no velocity. And it turns out that we can use the equations. Acceleration is force divided by mass in either reference frame. So in the two reference frames, not everybody agrees about the velocities, but everybody agrees about the accelerations and everyone agrees about the forces. So that's kind of a fundamental idea in classical physics as to how that works. Now, there was this reference to the Earth and, how much of an acceleration does the rotation of the Earth introduce. So I went through and did a quick calculation using some circular motion formulas, and I ended up with an acceleration at the equator, 0.0339 meters per second squared. So it's pretty small. And as you move away from the equator, the acceleration effect is even smaller. Now there's an acceleration due to Earth's orbit, but it's actually much smaller than its rotational acceleration. So we've gotten away with treating the surface of the Earth as an inertial reference frame at constant velocity, and will likely continue to work that way. All right, so relativity has been around for a long time. What Einstein did with special relativity in 1905, a little over 115 years now that it's been around, is he changed the rules as to how relative motion works. There's still a fixed set of rules as to how things operate, but it's not as simple as adding and subtracting velocities. And that's what I'm trying to show with this example here, I guess. In classical physics, if we have a couple people, they're on a high-speed train, this train's going 100 meters per second, and these people are throwing a baseball out in the aisles, and they're throwing it at 10 meters per second one way and then 10 meters per second back the other way. Someone on the Earth's surface in a different reference frame sees the baseball going forward, not at 10 meters per second, but at 110 meters per second, because that's how fast the train is going. So the person in the other reference frame will measure a different velocity. Now that's not a problem. We said that measuring different velocities is expected when we move from one reference frame to another. When the ball is thrown back inside the train, that's measured as 10 meters per second in the opposite direction. But for the person outside, they will continue to see the ball move forward. That's because the speed of the train is much faster than the baseball. So I can take the 100 and add on the 10 meters per second to determine what the velocity will be observed to be when the baseball's being thrown in the forward direction on the train. When the baseball's being thrown backwards on the train, person outside in their reference frame will still measure the baseball going forward, but this time at 90 meters per second. So adding and subtracting velocities is kind of fundamental to working between different inertial frames. Now, this was all fine and good for hundreds of years until towards the end of the 1800s, electromagnetic theory had been in development for many years, and kind of by the end of the 1800s, there was this synthesis taking place, or even the mid-1800s, that introduced the idea of electric and magnetic fields and a propagation speed for the electric and magnetic fields. Electric and magnetic fields propagate at the speed of light. And so when researchers realized this, they realized that light was somehow connected with electric and magnetic fields. Now, the prediction from all of the formulas from electromagnetics is that there is this new physical constant, c, which is the speed at which light travels. Now, the problem with an absolute velocity like that is, well, it can't be the same speed in every reference frame. If we have our people back in the train shooting or sending photons at each other, they're shining flashlights at each other, and the photons are going back and forth and they're measuring the speed. On the train, they're measuring the speed to be c in both directions. What about the observer outside the train? Now, classical physics would say, well, it must be faster in one direction and slower in the other. But that's not what electromagnetic theory predicts. So the formulas from electromagnetic theory were just amazing in that they seem to predict all of electromagnetic phenomena. But they made this crazy prediction that everybody in every reference frame would measure light to have the same speed. So I even speeded up the train. Notice on the right, I put the train at 99% of the speed of light. And even at that speed, we're still expecting, or it's predicted, that the speed would be the same. Now that just, it's either a contradiction, it can't possibly be true, or else the other possibility is there's something going on here with how we measure distances and how we measure time intervals. And that's the approach that Einstein took. Einstein looked at the formulas of electromagnetic theory and said that it's pretty amazing. Einstein just thought it was a beautiful theory. So he asked the question of, what if this is correct? What would we have to do? What kind of modifications? How would we have to redevelop physics, mechanics, our understanding of distance and time, so that this would actually be the case? So that was kind of a starting point for Einstein, and Einstein was able to develop a set of formulas where distances and time intervals are not the same. Einstein said, look, the reason the people outside the train and the people inside the train are measuring the same speed is because speeds are really measurements of distance divided by time measurements, and if the people inside the train and outside the train, what if the distance that the balls are traveling are not the same? What if the people outside measure that distance to be shorter or longer? And then what about time intervals? What if time is not progressing at the same rate inside and outside the train? Now that sounds very counterintuitive, but it turns out it's right. We have just overwhelming evidence that that really is the way nature works. So what that means is, everything we learned in Physics 4a, we got to go back and take another look at that. We got to go back and take a look at what was happening in all of the classical physics formulas that we developed. They're all going to have to be altered a little bit. What we're going to find is that all the stuff we learned in Physics 4a was a perfectly good set of formulas as long as speeds were not large compared with this physical constant c. And so let's take a look and see how that works. A couple of the predictions that come from special relativity are referred to as length contraction and time dilation. So length contraction says this. It says that if I have an object, let's say a meter stick has a pretty well-defined length to it, 100 centimeters, if it's at rest. But relativity says that objects that are moving within our reference frame are not going to appear shorter, they're going to physically be shorter. They are going to take up less space. If I have a moving meter stick, now I used a pretty high speed here, I plugged in the value of 80% of the speed of light. So if I have a meter stick moving that fast, it actually turns out that the meter stick only takes up 60 centimeters of length, which sounds kind of crazy, right? But what does length even mean for something moving that fast? And length means if I simultaneously measure where the front of the object is and where the back is, I find that the distance between front and back as it moves through my reference system is consistently only taking up 60 centimeters. It's shorter. Objects are actually shorter as they go to high speed. Now, Einstein was able to come up with formulas that showed exactly by how much, by what amount, this is going to be shorter. The length contraction formula looks something like this. It says, look, if I measure the length of an object when it's at rest in my reference system, if it's moving past me, it's going to be reduced by this factor we call gamma. So gamma is going to show up a lot. So it's worth spending some time and getting a feel for how gamma works. Gamma is 1 over 1 minus v squared over c squared square root. So, and this actually just comes from, you can actually derive these formulas using some triangles. And there are some earlier sections in the textbook that go through some of these derivations. So if you do want to spend the time and go back and look at those, I'm going to say it's not required, but it's fine, you know, if you want to go back there. Just make sure that you're thorough on the other items that we're going to be looking at, actually using these formulas and applying them in different situations. So if I take a look at this gamma factor that we've now defined, it's just a function of velocity. Now, one of the features of special relativity is velocities are limited. There's no such thing as a velocity faster than c. Every velocity we ever measure is going to be somewhere between 0 and c. It's not that we can't get things to go that fast. There's never going to be a velocity measured faster than c, because we'll never measure the way that the distances in time are connected. We'll never measure a distance divided by a time that has a higher ratio than c. It's the way space and time are put together. The way space and time are interconnected, there's just no such thing as going faster than c. So on our graph, v only includes this range of values between 0 and c. Now the way gamma is defined, when v is equal to 0, gamma is equal to 1. And so I've plotted that on the graph here. There is this asymptote at 1. And then what happens is, initially, at low speeds, gamma is essentially 1. You know, at everyday speeds, all of the speeds we're used to, gamma is essentially 1, and this length contraction effect just doesn't show up. It's not very noticeable. We would have to do really careful measurements to pick it up. But as the objects go faster and faster, the length contraction effect becomes quite noticeable, and as you actually approach c, gamma goes to infinity. So it says if I let my meter stick go faster and faster and faster and faster and faster, it's going to get shorter, and there's no limit to how short it can become. As that speed approaches c, the meter stick will approach taking up no length at all in the limit as it approaches c. Kind of a remarkable prediction. Now, along with length contraction, and I put a couple numbers in here, I guess, real quickly here. Half the speed of c, gamma's at 1.15, 80% of c, gamma's at 1.67. Add your own numbers to the table. We'll be doing a lot of examples where we get to relate v and gamma. You're going to be using this formula quite a bit. Given a velocity, what's the gamma value? And then we also want to be able to switch back. So given a gamma value, what's the velocity? So for example, what would I want the velocity to be if I wanted a gamma of 2? And by using this formula, I can see that the velocity I would need to travel at to have the meter stick reduced down to a factor of 2 would be 0.866 c. So I'd have to go just a little faster if I wanted to bring it down to 50 centimeters. Okay, so useful formulas. Now, in addition to length contraction, there's a related effect, and that's time dilation. And that says that if I'm in the reference frame where I am measuring the time of progression, or the time interval of an object, that's going to be a shorter amount of time. And if I have that time being measured in a moving frame, the time is going to increase. The example I have here is this. Maybe if the example will help clarify this. There are a lot of fundamental particles in nature. I guess, I don't know if they're fundamental, but they are not stable. They undergo radioactive decay or decay of some sort. One of these particles is called a muon. So it's like a heavy version of the electron, but it has a lifetime of 2.2 microseconds. On average, these muons only survive for a very short period of time. Now, that's the amount of time they survive when they are generated in our laboratories at rest. But if we generate a beam of muons that are moving at high speed, we can have them survive longer. So in fact, what I decided to put in here was a factor of 2. You know, what would it take to have a muon survive twice as long? And if I want to double the lifetime, according to this time dilation formula, what I want to do is I want a gamma to be a factor of 2, and I want to generate these muons in a way where they're moving at 0.866 times the speed of light. Okay. Now, what's going on in the muon's reference frame? So if I'm the muon, in my reference frame, only 2.2 microseconds go by. But in the frame, watching this muon zip by, the muon survives for 4.4 microseconds. So it's different time intervals predicted in relativity. Now, this first example, actually, it is the muon, so it's just with some different numbers. In the book's example here, they're going to have the muon moving at 60% of c, and they've actually given this in meters per second. Lifetime is 2.2 microseconds. And they're saying, you know, what would now be the average lifetime of a moving muon, and how far would it travel? So here's our first example. Again, the muon is it's a heavy version of an electron. It's about 200 times heavier, but it's not stable. So it undergoes decay, and we can measure these, and you know, we've been measuring these for, muon was probably discovered 80, 90 years ago. We've been measuring these properties for a long time now. Here's a bunch of muons moving. Here's some, you know, if it's at rest, the lifetime would be this value. So they're saying 0.60 C. Well, I can plug that into my gamma formula. I find out that at 0.60 C, I have a gamma value of 1.25. So the lifetime of the muon is going to be extended by this 25%. When I put that value in, I'm using this symbol T because that symbol gets used to represent the lifetime of a unstable particle. And so I'm going to put that gamma factor in and say, you know, if it's moving past me, in my reference frame, I'm going to measure the time to be longer. The time is going to be longer in my reference frame than it is in its own reference frame. So that says that it now, in this reference frame, will survive for 2.75 microseconds. And then I can go back and just do d equals vt. So if the velocity is... oh, I'm sorry. The velocity's here. So I've got the time, the 2.75 microseconds, the 0.60 c, 495 meters. So this particle, which only lives for a few microseconds, is able to travel 495 meters. And we measure this. You know, in laboratories we can measure these effects. A muon moving quickly through our reference system, through our lab reference system, survives longer and has a longer lifetime. Now, we routinely generate muons in our labs these days that are moving at really, really high speeds, 0.99999 C. I put something in here that happens to be at 0.999 C. That gives me a gamma of 22. That gives a lifetime of now 49 microseconds and a distance of 14,750 meters. Okay, so as you bring the speeds of these muons closer and closer to C, the gamma factors go up. Remember, there's no limit to how large gamma can become. And so gamma can become infinitely large, and in our reference frame, with these muons zipping by, they can now live for much longer periods of time. Now, another example here, let's see, is looking at a car moving at 100 kilometers per hour. So if you're thinking, hey, this doesn't happen to me when I'm out driving my car, I don't notice these time dilation effects. Well, let's see what happens. If a car travels at 100 kilometers per hour, what effects are we going to be able to pick up? So here is the time dilation effect. So I took the 100 kilometers per hour, converted that into meters per second. So that's coming out at 27.8 meters per second. And then I plugged that into my gamma formula. And you know, when I did that, my calculator said 1. Now I know that gamma is going to be a little bit larger than 1. Why is my calculator telling me that gamma is only 1 at this speed? Well, what I can do is I can use an approximation technique. You may recognize this from series expansions that you've learned in your math classes. So what we can do is say that if v squared over c squared is much smaller than 1, we can approximate it as 1 to plus the exponentiation factor times v squared over c squared. So we're using an approximate formula, which is going to work really well. This formula is going to give us a very good approximation. So at really low speeds, you know, if I put these numbers in my calculator and they're telling me that gamma is just equal to 1, then what I probably want to do is use this approximation. So that's what I'm going to do. And it turns out that the gamma factor for my car, you know, driving down the highway at 27.8 meters per second, is 1 plus 4.3 times 10 to the minus 15. So gamma is actually 1.00000000000000043. And that's why it drops out of my calculator. My calculator doesn't keep numerals to this level of precision. So if the driver has 10 seconds go by, then the observer outside, during that same 10 seconds for the driver, would observe an additional, 43 10 to the minus 15 seconds. So that's the timing difference in these situations. And that's why everyday situations, it just doesn't come up. Okay. Once things are moving fast, though, you have to use relativity. When I was in graduate school and a postdoc doing research as a physics researcher in high-energy particle physics, we just used relativity all the time. All of the particles that were involved in our experiments were moving at really high speeds, many of them very close to the speed of light, and we just had to use relativity on everything. So you just kind of realize relativity is for real. Now, it's been proposed, it says here, the time dilation effect would enable astronauts to possibly travel really long distances. So you could have planets that are hundreds of light years away, but the astronaut, if they're traveling near light speed, depending on how close to light speed you're traveling, you could have, for the astronaut, maybe only a few years go by. Now, when the astronaut returns, if the astronauts head out to some planet, it only takes a few years for them to get there, and then a few years to get back. But it could possibly be that hundreds of years have passed back on Earth. So that's kind of an interesting thing to think about. It turns out bringing a spaceship up to those speeds is beyond any energy sources we now currently understand. But if that were to happen, we would start to see these timing paradoxes that take place. Now this slide is telling us that because the astronauts are the ones that went out, they picked up speed, they accelerated, and then they slowed down and reached that planet, and then they turned around and came back, that it really is the case. The situation is not symmetric, and that the amount of time that takes place on Earth would be very different from the amount of time that has taken place for those astronauts. Now here's a problem I added in. I just decided to come up with some numbers. Let's say that we are traveling to some distant planet 20 light years away, and I wanted to also put an example like this in here so we could practice using the length unit of light years. So the light years are can be written as c times year. This turns out to be really handy. What we can say is, look, if I've got a spaceship traveling at 0.95 c, and it's got a gamma factor of 3.20 is what that works out to be. The length, the distance that I'm traveling to the distant planet is 20 light years. The time it's going to take, I can do as L over V. That's 20 light years over 0.95 c, and the c's cancel. So that's the idea here, is to get the c's to cancel out. And the only unit that's left here is years, and I came up with 21.1 years. So that's pretty fast, 0.95 c. It's a pretty good gamma factor, 3.2. But in the Earth frame, this is going to take 21.1 years. So if they travel out and come back, it's going to be at least 42 years that pass by in the reference frame of the Earth and the distant planet. But now let's move over and ask what's happening in the spacecraft. So in the spacecraft, what we're going to find is in the spacecraft, the Earth is moving by. The Earth is moving away from the spacecraft, and the planet is approaching the spacecraft. Now, I can use length contraction because the Earth and the planet are in a different reference frame. I can use length contraction to find out how much distance is there between the Earth and that planet in my reference frame. So instead of the Earth and the distant planet being separated by 20 light years, in the rest frame of the spacecraft, it's only a 6 light year journey, or it's only a 6.25 light year distance between the Earth and the planet. So the planet is only 6 light years away. Once the spacecraft is up to speed, that actually brings the planet closer. It literally now is only 6.25 light years away. And in the spacecraft, we can now find out, well, how much time is it going to take? Well, if it's only 6.25 light years, and we're going to use the same relative speed. So both reference systems agree on what the relative speed is between them. So this time, I'm going to put in a different distance and put in that same speed. Turns out that only 6.6 years go by in the spacecraft. So in this case, they head out for 6.6 years, they spend the weekend, they get fuel up the spacecraft, and then they come back home, and maybe 13 years have passed for those astronauts. The astronauts are 13 years older, but their friends back on Earth are 42 years older. Okay. Again, as you approach light speed, as you get closer and closer to the speed of light, the gamma gets larger. There's no limit to how large gamma can get. Now, it does require more and more energy. So it turns out that the amount of energy required is proportional to gamma. Even though as you get to higher and higher gammas, you're getting closer to the speed of light, but you're not changing your speed that much. It still takes more and more energy to boost the value of gamma. So it ends up taking a lot of energy. We'll do an energy calculation and see how practical this might be. But, that would be a great experiment to try out. See how those times compare. Now, time dilation effects have an effect on GPS satellites. These global positioning systems that we have in place now, where there's a whole network of satellites that are orbiting the Earth, and they have atomic clocks. They have really high precision clocks on board, and all these satellites do is send out a regularly timed signal. They just send a signal at regular time intervals. Well, the passage of time for a satellite that's in motion is going to be different than the passage of time back on the surface of the Earth. So we're going to have to take into account these special relativity effects of time dilation. So special relativity says that time is not progressing at the same rate. The timing going on in the satellite won't match the clocks on Earth. We're going to have to account for that when we program our GPS devices. Now, there's a second effect which we're not covering in this chapter. So in this chapter, we're looking at special relativity effects. There's a more general version of relativity that Einstein developed, spent an additional 10 years working on this, and in 1915 came up with general relativity. Turns out that the gravitational field, or what's called the gravitational potential, also has an effect on the passage of time. As gravitational effects get larger, time slows down. And so time is actually going to be progressing, due to this effect, faster on Earth compared with in the satellite. So let's take a look and see which effect dominates, how large these two effects are. So here's Earth. Here is this satellite in orbit. And this satellite, it said, was moving at 4,000 meters per second. The orbital radius, it turns out, for these satellites is about 25,000 kilometers. So I added that in. And then here are our formulas for time dilation. Now it turns out this is a small effect. Even going 4,000 meters per second, it's not going to be a very big effect. That's not very fast compared with the speed of light. So for the gamma value, I'm going to use that approximation that we had developed and said that for speeds that are much, much less than the speed of light, I can say gamma is 1 plus 1/2 v squared over c squared. So I put the numbers in. There is c, there is the speed of the satellite. The gamma factor, based on special relativity due to the velocity of the satellite, turns out to be 1 plus a little tiny bit of 8.9 10 to the minus 11. So that's what it looks like if you write it out. Now I wanted to get a feel for what that tiny additional factor would result in. So I said, okay, 1 day is 24 hours times 60 minutes times 60 seconds. And taking that small fraction, the timing difference between satellite and surface of the Earth works out to be 7.7 microseconds per day. So during the course of 1 day, 86,400 seconds, the timing between the clocks on the satellite and the clocks on the surface of the Earth, those will be off by 7.7 microseconds. The clocks on the satellite are going slow. Now, that's going to disrupt our GPS system. If we want the GPS system to give us an accurate location as to where we're located, based on these satellite signals, we're going to need things accurate. I think it said to 1 part in 10 to the 13. So anything 10 to the minus 13 or larger is going to have an effect, and this is significantly larger. So this definitely has to be taken into account for a GPS system. Well, let's move on and take a look at the general relativity effect. So we'll continue on, GPS satellites. Now the gravitational time dilation effect, the formula basically is kind of the same. T is equal to gamma times T, where the two T's are representing the two reference systems. The effect from general relativity due to the gravitational field is given by 1 minus 2gm over c squared over r square root, where big G, you guys remember big G, right? Our gravitational force constant, which I didn't write down here. I should have. Let's see, 6.67 10 to the minus 11 newtons meters squared per kilogram squared. Okay, and then big M is the mass of the Earth. So 6 times 10 to the 24th kilograms. C is, it's the speed of light factor. What we're going to find here is this, too. As long as C keeps coming up into every calculation we do, C is presumed to be the speed of light, but C is much, much more than just the speed of light. C is going to turn out to being our space-time conversion factor. We'll see more when we get farther into the slides, but C has a pretty significant meaning as far as how space and time are configured. What is the structure of space and time? So anyway, getting back to this formula, I used an approximate formula for this to get rid of that square root sign. And then what I wanted to be able to do is write it the same way as before. 1 minus, this time, gm over c squared over r. And at the Earth's surface, which is a value of 6,370 kilometers, that time dilation effect worked out to be 7.1 10 to the minus 10, whereas at the location of the satellite, it's only 1.8 times 10 to the minus 10. So both at the surface of the Earth and at the satellite, time is slowing down. But the timing slowing down is much more pronounced on the surface of the Earth. Now, using the same 86,400 seconds, which we had used on the previous page, we find out that the timing difference between satellite and Earth is 5.3 10 to the minus 10. How much of an effect is that going to be? Well, it turns out that's an even bigger effect than the special relativity effect. The effect here is about 46 microseconds a day. So the net effect from the gravitation, as predicted by general relativity, and the velocity of the satellite, as predicted by special relativity, works out to about 38 microseconds a day. That's how far off the timing would be between a clock in orbit inside the GPS satellite compared with a clock on the surface of the Earth receiving the signals from that. And so GPS satellites and GPS receptor units, a GPS device that we work from, need to be programmed to take that into account. So that's pretty real, right? That's something that's really happening. Okay, here's kind of a silly example, but it's one that our author likes, so I'll take that back. Here is a painting. It's 1 meter in the vertical direction, it's 1.5 meters in the horizontal direction. What happens if that painting moves past us at 90% of the speed of light? And if that happens, I'm not even going to see it, right? Because it's going to go by so fast. Anyway, if we have an object with these dimensions, and it's moving in this direction, what this problem's trying to drive home is that the vertical height is unaffected. So the length contraction effect is only taking place in the direction of relative motion. So if this thing's moving in this direction, I'm going to get a significant shortening here, and we can work from our length contraction formulas. We can solve for gamma. So what this says is here's a rectangle and A is 1.5 meters and B is 1 meter. If this rectangle is moving past me really fast, what will happen is I'm now calling A prime, is going to be this length contracted distance. And so I just have to divide through by gamma to find out what that's equal to. And I used the speed of that they gave us, 90% the speed of light. The gamma factor worked out to be 2.29. A prime turns out to be 65.4 centimeters. So that's quite a bit of shortening, but B prime is just B. So that's supposed to be B prime. Is just equal to B. That's going to be the 1 meter that we had before. Okay, that's the kind of problem you want on the midterm, right? Something like that. All right, here's a more extreme case. Let's take a look at the fantasy super train. So it says a very fast train with a proper length of 500 meters passes through a 200-meter long tunnel. Let's imagine that the train speed is so great that the train fits completely inside the tunnel as observed by someone on the surface of the earth. That is that the front of a train, just as the front of the train is emerging from the end of the tunnel, the back of the train is going into the tunnel. How fast is the train traveling for this to happen? So you're thinking, oh yeah, relativity makes this a practical problem. So here's the train at rest. It's 500 meters long. Here is a tunnel. It's 200 meters long. How am I going to fit a 500-meter train into a 200-meter tunnel? And I'm going to do that by having it go really fast, right? So let's do this. Now I'm starting with solving for my gamma factor. If I want a length of 500 meters to length contract to 200 meters so that it fits, I'm going to need a gamma factor of 2.5. And using my gamma factor velocity formula, that tells me that the speed I need to have that train going at is 0.9165 times c. Now, at that speed, this train would go all the way around the circumference of the Earth several times in just a second. So, I don't know that this is necessarily a practical problem, but let's just go along with them. Let's humor them. And so, I want a train going this fast. And if we do, if we are able to get a train up to this speed, this would really happen. So event A, I'm going to define what we call events. Event A is the front of the train leaving the tunnel, and event B is the back of the train entering the tunnel. And we want to make sure that those happen at the same time, and they will if we're traveling at that speed. Okay, so events A and B are going to be simultaneous. Yes, the train fits inside the tunnel. And it's going really fast. All right, let's turn this around now and ask another question. Well, what's going on in the train? Because if the train is moving at constant velocity, then the train can consider itself, the people on the train can say, well, we're in our own reference system. So in our reference system, we're at rest, and out in the distance, we see this tunnel coming towards us, and the tunnel's approaching at 0.9165 c. How long is that tunnel going to be? Well, it's going to be length contracted. The tunnel in the reference frame of the train is going to be shorter. It is going to be length contracted, and it's going to be length contracted by that same 2.50 factor. So the tunnel coming towards the train is only 80 meters in length. And I know you're thinking, well, if the train's 500 meters long and this tunnel of 80 meters is coming by, the train doesn't fit. So in the reference frame of the train, the train is never fully inside the tunnel. The tunnel moves to this position, and that's event A, and then the tunnel keeps moving to this position, and that's event B, and then the tunnel moves past the train. So in this reference frame, the train was never fully inside the tunnel. Now that's kind of interesting that a statement like that is true in one frame, but it's not in the other. But relativity says that's okay because they're both going to disagree about how much time there was between events A and B, and they will also disagree about the distance between events A and B. So let's take a look here, see if we can predict how much of a time delay in this reference frame there is between event A and event B. There is 420 meters of distance between when the tunnel first, when the back of the tunnel first reaches the front of the train until the front of the tunnel reaches the back of the train. I get that by taking the 500 meters and subtracting off the 80-meter length of the tunnel. So in order for that tunnel to have traveled 420 meters and it's moving at a speed of 0.9165 c, that's going to be a time difference or a time delay, a time interval of 1.53 microseconds between the two events. Whereas in the other, so these are the numbers we're getting here, this is the timing. The distance between the events here is 500 meters. If we go back to what was happening for the observers in the reference frame of the Earth, the two events happened at a distance of 200 meters, not 500 meters, and there was no time difference between the two events. So here, the separation distance 200 meters, the time interval is 0. Here, the distance interval is 500 meters, the time interval is 1.53 microseconds. Welcome to special relativity. That's how nature works, apparently. So, do you guys have any questions about this? So anyway, stop by during office hours. These are the kind of really kind of fascinating examples that come up in relativity, and they're kind of fun to think about. And again, if you're in a field where things are moving fast, you have to be able to use relativity to be able to correctly understand how to set problems up and how to calculate for different physical quantities. All right, so here is the book's resolution on the train and the tunnel. I think we've already talked about it pretty thoroughly. Okay, oh actually they're asking here, aren't they? Okay, and then they're moving on. Let's try one more example here, and then we'll take a break. Remember, back in back in the, kind of the beginning of our discussion here, we were talking about velocity addition. You know, when I add velocities together, how do I add them properly? And it turns out that that simple rule for just adding the velocities together or subtracting them, that can't possibly be the whole story. So let's do this actually. Let's take a break now, and we'll come back and we'll take a look at how are we going to add velocities together.